In Unit 2 of COMP526, we'll look at some fundamental data structures, which are often covered in undergraduate algorithms and data structures classes. I'll just give you a very quick rundown showing you the gist and the basic results from those that we'll use and build on in other units. This will be very fast-paced if it's the first time you see the topics. If it's a refresher, then maybe at some intermediate stages you'll get bored a little bit, but at least it's fresh in your memory then for the upcoming units. So specifically, what I want you to take from this, the distinction between an abstract data type and its implementation, something we'll talk about. Then a list of concrete abstract data types that I think are useful to know outside of this unit as well, outside of this module. We'll specifically look at a few implementations, specifically these that are listed here. We'll go through those, so no need to discuss them in detail now. These are basically the upcoming sections. We'll start with very basic data structures, stacks and queues, and then basically look at two others, binary heaps and binary search trees. Recall from yesterday, from Unit 1, what we're working on at the end of the day is our abstract model of a computer, the random access machine. And we basically have just one big piece of memory, but we assume that there's something like a memory allocation system. So you can just wish for a new instance of an object, and your wish shall be granted. The operating system somehow handles this for you. There's a few, basically these work for every programming language. We'll give you access to some of these features. Because we're doing most of it in Python, there's a few caveats. So we'll assume that we can do basic pseudocode on our RAM, discussed this yesterday in detail, that we can create arrays and we can create objects. Now, much of this you can just do in Python and pretend it is a RAM for all intents and purposes, except for arrays. Python doesn't really nicely have arrays. I know this statement is technically not quite true. There's a part of the standard library that gives you access to more low-level arrays. It's just not a very intuitive way. And the standard thing you use in Python are lists. So if you just write these square brackets, that would be a list. And the object that backs it has many features of an array, but it is dynamic in size. So you can change the size. Whereas arrays are always of a fixed size that you have to specify at allocation time. We'll actually look in this module at what Python does under the hood, because Python does run on a computer where the operating system just gives you fixed size arrays. There's no such thing as a resizable array provided by the operating system. And yet Python gives you this abstraction, and we'll look at how this is done. It's a very standard trick. So it's just a point to remember. We'll mostly write code as if it was Python, but it's not really a random access machine if you write Python code. So it means some things that you can write in Python in a single line or a single built-in function doesn't actually take constant time. Classic example, if you have a very long list and you insert something in the middle, it's linear in the size of the list. It's not constant time. It's a very expensive operation if you do it on a long list. That's just something to be mindful of. With that said, let's look at our first examples of some data types, abstract data types, and implementations. And before we get to that, I should finally tell you what I mean when I say abstract data type. So here's a list of the properties of the two. An abstract data type tells you what the operations are that a certain structure is supporting. It tells you what should happen, but not how it's done. So in a way, you can compare it to an interface or these abstract base classes in Python, which is maybe a bit more of an esoteric feature that not too many people use all the time, but Python has something like this if you want to read it up. The basic idea is you tell the programmer, someone who uses your data structure, what they can do. And you don't tell them how it's done, not because you're a mean person and don't want to give your secrets away, but because that means you can implement it in a different way and the user can't really notice because you haven't told them. So you can swap out implementations afterwards. In programmers' terms, people call this a drop-in replacement for some part of the code. Right? If you program just against the public interface of a data structure, which is in older terms, so this term predates interfaces in modern languages. That's why people stick with abstract data type. We can debate if the term is great, but I'll stick to it because it's very standard in textbooks and so on. If you program just against these public methods, then you can swap out how it's done under the hood, and it shouldn't change your program. So that's the essence of producing reusable code, which is, as we know, is one of the only ways how we can tame complexity in programs. Good abstractions and independence between parts. But on the other hand, at some point, you have to show how things are done, and you have to implement them if you actually want to run them. So data structures are fleshing out all the parts that are left open. I said this last time already, so they tell you exactly how data is represented and how these operations are implemented, what algorithms are used for those. The rough equivalence could be in Java, you have interfaces and then classes implementing an interface. In Python, you can have a subtype of these abstract base classes, where it's a little less direct. What I want to point out is in Java, for example, an interface is merely syntactical. It just tells you what the method's signatures are, the names of the functions and the types of the parameters, and that's it. It's very shallow. It doesn't tell you anything about the meaning. Maybe you have Java doc, a comment about it, or doc strings in Python. You have some natural language text that explains to the programmer what that thing should do. But this is not enforced on the technical side. We'll be a bit more strict. We require that our abstract data types tell you exactly what the meaning of these functions is. Without having a formal way to check it, we just assume that you do this as a human. I already talked about why it's useful to have abstract data types, so you can swap out the implementations. There's another one that I haven't touched on, which is a little less direct. But if you keep things generic and you prove a general result about the generic thing, it's more applicable. It holds for everything. So sometimes you can prove a lower bound, which is an impossibility result. A lower bound means you cannot possibly do better than a certain running time, for example. And we'll see an example for sorting that you've seen in undergrad classes if you've done those in computer science. But that's only really effective if you have a level of abstraction. So we'll come back to that, not so much today, but that's another advantage of staying a bit more abstract. Now there's also a downside that I just want to humorously point out with this picture. Sometimes, if you enforce a certain abstraction and a certain weird interface, it might mean you make your life more complicated. Like in this case, you just want to get some water, but then you had to build this weird structure to have it look like a nice water tap. Whereas if you need the water further away, you could have just taken the hose and carried it over. But that's hidden by the abstraction. If you just look at the tap from the front, you can't move it anymore. This sometimes happens. So abstractions are great, but it's important that you're able to look behind them, because sometimes if you crack them open, you get a much better solution. So don't slavishly follow abstract data types, but it's important to know them because they're the language people use, and they're generally useful. All right, enough of talking for me for a moment. Let's see if that has sunk in and if you know a few of these already. I guess for those where you don't know what the name stands for, it's a bit, you can't really give a sensible answer either way. And I guess you'll just have to guess. We had 126 people vote on the welcome thing, and then 89 for the attendance code. If you want to do me a favor for the attendance code, always send this got it so that I know how many people we have in the room. It's a bit easier than for the next section. So we're already at 86 again. 89. I'll see if we can get 100 full again. It's a nice number. Two more. A few people are still typing. Goodie. I'll start showing some results. I don't want to discuss this in too much detail. We talked about stacks. Now, several of these terms, as I said, if you don't know what the term stands for, you can only guess. We'll come back to those. So I'll just leave that without much comment. But that's the right answer. Basically, all of these we'll touch on in this unit, so you'll see them. And the rest, I mean, ADT is just the abbreviation. Right? But the others are implementations, are data structures. Let's have a look at, pardon? Which one? Ah. Let's see our first. Let's take it offline, okay? Let's look at a first ADT for this unit. It's a very simple one. It's a stack, and as the picture shows, you can put things on top, and you can get the topmost item out. Let's assume there's no way for you to balance and pull out the book from the middle. So you can do top, get the topmost item. You can put another book on top, and you can say pop, which removes the topmost. And a few helper methods that are not so important. So let's see just that everyone's clear on this, but I'll do it quickly on this one. So you have some stack of this type with one at the top. So it looks like this. Yeah, looks like you got this. So you can still put in your answer, but you may see that the vast majority came down to the same thing. So if we do one pop, then we remove the 1. If we do another pop, we remove the 2. Then if we push 1, again, we put the 1 here. And so in the same convention, like I did it here, reading from top to bottom, we have 1, 3, 4, 5. So that's this one, right? Good. So that's how stacks work. Again, remember, this is an abstract data type. It only tells you what is supposed to happen. It doesn't tell you how it is happening. And there are different ways how to do it. I want to just briefly show you the two main ones. The easiest one is with a linked list. And if you've seen this before, that's all you need to know. I wanted to show some well, Python-inspired code. It's not Python by the syntax. We need a certain class that has two fields, a value that we store, that's the value on the stack, and a pointer to the next thing. And then the way this works is we have a pointer that points to the topmost item on the stack. And then this item has two fields, right? It has the value and it has a pointer to the next item. So it points down to the next thing. And then maybe another one. And at some point, we stop. So this is pointing to null. I'll just draw this like that. Then that signals the end of the stack. And now if we want to get the top item, we just follow the top point and return the value that we find there. If we want to push a new item, we add a new, and it doesn't matter where this is drawn. It could be over here. So we add a new item 0. So we create this new node, which points to wherever top pointed to. And then we reset top to now point to this new item. And that way we have added a new element on top. And pop works in the opposite way. You first get the topmost item, and then you just set top to wherever that pointed to. So you rewire it like this. If I'm doing the pop again instead of that. And you return the old item in this implementation. That depends on how you do it. So in a way, this is still around. We still have this element that points to the now top element. But the data structure only cares about what follows from top. Now, what can we say about this implementation? So that's a data structure, right? It implements the stack abstract data type. Just to get the terms straight. What's good about this? Well, if we have n elements on the stack, we probably need to store those n elements. So we will have linear in n space overall. That seems inevitable. Also, all operations just take constant time. If you just go back to the code, all they do with our assumption on the random access machine takes constant time. What's a bit unsatisfactory maybe is that we have an extra overhead of space. For every element, we store a pointer, which means we have linear overhead in space, and we could try to get try to reduce that at least. So one way to do without pointers is to use an array instead. And so if you draw an array, not in the usual way left to right, but kind of flipped 90 degrees, you could imagine you have a variable top that just tells you at what position is the current top of the stack. So maybe you have these numbers again. And then these are indices in the array. 0, 1, 2, 3. And then top just stores the index of the topmost element in the stack. And you can implement the other operations similarly. If you want to push something, you write it to the next free cell and increment top. If you want to pop, you just decrement top. So that's all relatively easy. But there's a problem. If I have an array, I told you earlier, it has to have a fixed size. So I have to allocate an array of a certain size. I need to know it up front. So if I keep pushing onto my stack, I eventually have the entire array used up, and then I can't push anymore. And in a way, for a strictly array-based implementation, that's impossible to solve. So we have a fixed capacity, and the user has to promise us that they will never push more elements than the capacity of this array is. But we need to know this up front. So it's not strictly a full implementation of the abstract data type. And also, if you look at it, we always need we always need space C. Even if we just have 5 elements on the stack, C might be much bigger. So we try to save space, but it's not necessarily so much better now. But the operations take constant time, and in practice, they're usually faster than doing a linked list. Those are the two different ways to implement arrays. Basically, that's all of the ways that will. That's the two ways to implement stacks, either linked list or an array. That's the two main ones. And these are also usually offered in some form in the standard library. Let's look at the same time at a small relative of the stack, which is very similar to implement. It has a slightly different notion. That's the queue. It again is some data structure. So here again, that's the abstract data type. It has two operations, inQ and dequeue. You can add a new element, and you can take the front of the queue. But of course, the notion in a queue, if you're doing this in the proper British style, you inQ at the end, and dequeue from the front. You're the next to go into the store, whatever that is. So the abstract data type is different. The order of elements that you obtain from getting elements out of this data structure is different from a stack, but the implementation can actually be very similar. And I'll leave that to you to figure out, or you can watch the video on it if you haven't seen it. The two same options exist, and they have essentially the same trade-offs. Sometimes it's convenient to have an abstraction that captures both of these. What they have in common is that they're somehow a collection that you can put things in and you can get things out. That's what stacks and queues both do. So they both have an insert operation, even though it has been given a special name. And there's a way to get an element out. In the general bag, you just say delete any element, and you don't make any guarantees. So this is less strict than a stack or less strict than a queue. So you can take any implementation of stack and queue and say, that's a bag. It's a special kind of bag that gives you a specific order. But if you program against the interface of a bag, you're promising you don't make any assumptions on the order. This also exists under the name collection in standard libraries. Usually, so there's not really a way to implement bags in a more efficient way than stacks or queues, but it can be useful for you as a programmer to express that what you need is just a bag. You don't care at all about the order of removal of the elements.